What most people think about when mentioning carbon dioxide is probably this: the fossil industry. And that's logical, since the total CO2 emissions from fossil fuels and industry has reached over 37 billion tons in 2021. In an attempt to combat this, the use of renewable energy sources has increased during the last decade. A reliance on fossil fuels, however, will continue to exist. Moreover, the rapid depletion of resources by overconsuming them becomes an increasingly important issue for the present and future generations. That is why carbon capture and utilization technologies, CCU in short, are acknowledged as a crucial component for decarbonization strategies. CCU is a concept where CO2 is captured from emitters and used as a feedstock for conversion into other products. Therefore, CCU can turn a linear economy of extraction, conversion and emitting into a circular economy of capturing, converting and capturing again. Next to the advantage of creating economic value, CCU can decrease the CO2 concentrations in the atmosphere in two ways. 1. By decreasing the CO2 emissions at the source itself, and 2. By increasing efficiency and replacing conventional fossil-based raw materials. So all in all, CCU technologies provide a substitute for fossil resources and as a result slows down the depletion. Another way to reduce fossil fuel emissions and limit climate change is by the substitution of fossil fuels with biomass. In many climate impact assessments, like carbon footprints or life cycle assessments, the CO2 from these biomass stocks is most often neglected. This neutrality assumption is based on the general notion that the carbon that is emitted was first taken up to form the biomass. Therefore, the sequestered and emitted CO2 cancel each other out, resulting in a net zero emission. The view that biogenic carbon emissions do not contribute to climate change has however been debated for a long time. Although the fossil industry emits more CO2 than the biogenic one, the gas concentration is much lower. While fossil emissions average between 3 to 14% CO2, the biogenic sources can reach up to 100% purity. This higher purity can reduce the cost of capturing and post-treatment. Therefore, the combination of carbon capture with biogenic CO2 could be a very beneficial solution. This combination is defined as bioenergy carbon dioxide capture and utilization, BECCU, and can be applied in many fields, like bioenergy processes such as combustion, gasification, anaerobic digestion, or alcoholic fermentation of biomass. BECCU enables a circular use of biogenic carbon and is CO2 neutral. Although the amount of literature on biogenic carbon capture is still limiting and most technologies are still in the developmental stages as of 2022, the results published from case studies are indeed very promising. A real case wine fermentation carbon capture and utilization system has been successfully tested and scaled up at a medium-sized winery in Spain. At global level, this system could capture 2 megatons CO2 per year, and when used to replace soda ash, this would even lead to an indirect emission reduction of over 5.4 megatons CO2 per year. Another case study looked at the application of BECCS in 110 existing Swedish biomass and waste-fired combined heat and power plants. They estimated the potential annual reduction of up to 16 megatons CO2, corresponding to 25 to 40% of the total CO2 emissions from all sectors in Sweden. This study, however, only looked at the storage of the captured CO2, so the direct and indirect reduction is potentially even higher if the captured CO2 were to be used in other industries. So, does biogenic carbon capture has the potential to reduce fossil CO2 emissions? Yes, and even in a multifaceted way. There are more than enough industries in which BECCU could be implemented, and at the same time the captured CO2 could replace carbon from fossil origin. But for now, the developmental stages are often too low.